I did research on AI, and it started kind of around 2014. I don't know if people in this room still have memories how it was in 2014. 2014, in the ancient past, people thought maybe, just maybe, you can make neural network translate between English and German. That was the state. And when you went to the Google Translate folks, they would tell you, nah. Like, maybe you can write a paper, but like, they're never going to translate well. And the workhorse back then was called RNNs, actually LSTMs. But so the way they worked is like you put words in, and then gradients would propagate on these long chains, and then you would start spitting out the words in the other language. And there was a paper by my colleague Ilya Sutskever, the other Ilya, was kind of like, look, this can actually work really well. And really well was still worse than the usual phrase-based at that time system that just, did word by word and then combined that. So that was the state in 2014, and generally, people did not believe very much that neural networks can do much more than recognize cats. So then this transformer thing came. It came after, so the RNNs started to be good at translation, and through a lot of personal connections, we convinced Google Translate to like actually use them. And they were like, wow, if you make them big, it works. So then we could, okay, but they're slow and unwieldy, so you could work on architectures, and we got to this transformer thing, which suddenly, A, worked much faster, and B, started translating much better. So, in translation in English, German, you measure this thing called BLEU, and like 23 was a very high BLEU score for English German, and like around that time the joke was like you could get a PhD if you got 1 or 2 BLEU up. So the RNNs, the other neural network got it to like 25, and then a small transformer was 27, and the big one was 28, and then soon thereafter it was 29, and and human translators are 32, so that's kind of done. And then people were like, oh wait, but maybe instead of translating, we'll put like the whole internet into this model and see what it learns. So at OpenAI, people did this. You see, this transformer had like this thing called an encoder and a decoder, where it took the input and output. And kind of at that time, there were two schools of thought. At OpenAI, they only took the decoder. So there was only output, and it, of course, can read what was there before. And it was called GPT. You just predicted the next word on the whole internet. And yeah, it worked pretty well. There was the other thing called BERT, which used only the encoder. Like you made some blanks and predicted that. And Google used this for a long time to make your searches better. So both kind of worked. The GPTs stayed longer. When you wanted to build like a really big models, there was one problem. How do you know your training is right? Because when you're doing deep learning, it's a lot of hyperparameters to tweak, and maybe you have a bug and stuff. So do you know, if you want to train a model for $10 million, $100 million, $1 billion, do you know how it should look? Well, you know. That's the lucky part. Because so every of these curves is one training run of a model. But it's a small model, so you can do a lot of training runs. And you see they look very regular. So you know how your training run of a big model should look. That was called scaling clause. And that's the reason we can be here, because without it, nobody would have put enough money to get here, right? And then, so come 2022, you take a bigger model. This was GPT 3.5. And you ask it to translate. And look, this was not trained to translate anything. It would just read the internet and predicted the next word. But of course it can translate. It can translate perfectly. And it can do a lot of other things, right? You can ask it whatever you want, and it mostly does it. And that was called ChatGPT. And I went to talk to some old friends last year, and I tried to tell them AGI, this thing, and they were like, so you mean ChatGPT? like they put anything in, and it gives them an answer, and it's usually reasonable. So what's the problem, right? But the problem, of course, is if you ask it to code, or to do something harder, like math, then it doesn't give you the good answer. It gives you a answer, but it's not right. But you need to realize that many people don't worry. Like, for many people, just the early chat is enough. But we do worry, right? So we were like, okay, but it should give you the right answers, and you can very easily see it's wrong if you try like math things. So in like the earlier chat models, you'd say something like Roger has 5 tennis balls, he buys 2, buckets of 3, how many does he have now? And it would just fail, right? Even though this is very basic, it would just get confused and fail. But there is a simple trick to make it work. Like in the example, you kind of show it that it should think. So instead of just giving the answer, it should generate a little bit of a thought process. And if you show it, even just by example, then it starts generating the thought processes and starts giving the right answer. Now, you don't want to give examples every single time. So the idea was like, can we train a model that learns on its own to think like in maybe long and interesting ways that will generate the right answer. So in the early stages, you train the models with something called pre-training, which is, here is the data, predict the next word. You know what's the next word. There is a gradient. Goes there. So here, you can't do this because you're sampling. That's not a differentiable process. So you need to train it with reinforcement learning. You're just checking the answer at the end. And then teaching the models to more often be correct. And this reinforcement learning is a little bit more tricky on the training side. But turns out like the most basic version of it, which is generate a lot of stuff when it gives you correct stuff, just fine-tune on this, it works. If you want a scientific description, the DeepSeek paper is great. And if you do that, your models, at least on math, they go up into the sky. And like Amy, for example, is not that easy, right? It needs like a fair bit of this reasoning. So this reasoning is not like 5 sentences. It's more like 1,000 sentences, right? It needs to go into these deeper chains of reasoning. So that's great. They actually do hard things. And then within this reasoning chain, you can not only generate tokens, but you can call some external tools. Like you can call tools like search, like Python, or maybe because these models now, they can also read images and output like coordinates on the screen. Maybe you go to a browser, click somewhere, read it. All of that can happen as part of your reasoning. And you can train it only with this reward of what you want to achieve. Like here, maybe you want to achieve that at the end it says a trip to Rome is booked. It's much easier to specify what you want to achieve than the whole process of where you should click. So this RL on models is a huge thing. I come a long time ago from complexity theory, so I kind of view this path as going over complexity classes. And like with this reasoning, we can do basically anything we can express in this chain of thought, which is a lot. But there is, I believe, one more problem, and I call it robustness. You can call it resilience as well. So our models, yes, they've learned reasoning. They often get us good answers. But what happens if they get us wrong answers? You know, the world is not just made of like, what can you do at your best? The world is also like, what do you do when you fail? And it turns out it's more important than we think. And I think for the future of agents in the next few years, it will be absolutely crucial. So what do agents do when they fail? I'm going to get to it. But first of all, one slide about technology, something that is easy to forget, but it's like the horse we're all driving on. And it's currently you can sample from a model like 100 tokens per second. And it used to be like 1. And these are like big models, and they used to be small. So this speed, like you wouldn't have all of these chains of thought or anything if you didn't have fast sampling, because nobody wants to wait an hour for your model to give you an answer. So the fact that the GPUs have gotten faster, the fact that we have a much faster sampling stack, all these code optimizations, like this hard engineering work through the years, make this possible. They also make video and audio possible, which opens like a huge possibilities for robots, for videos, for speech-to-speech. So this technology opens a lot of doors that I'm not talking about that may be, much more valuable than our math competitions. Remember that TVs run at 60 hertz. This is already faster, right? So in the early days, we were generating images like that. They were cute. Now you can go to Sora. It will generate you a whole video, high resolution. A lot has changed. Very soon, we're going to have games where like the graphics on your screen is generated in real time, and you're just playing, and you'll just tell how you want it to look, and it will just happen. It's quite magical. I kind of put it as an aside, but there's many interesting things to this technology that are not in the reasoning realm that I work on. But back to reasoning and agents. I asked Operator to do some shopping for me. It's like the standard example that's kind of on the website. And it bought me like some vegetables and stuff and eggs that I did not ask for. Why did I get eggs at my doorstep? The probability of the token was high. People who buy this stuff buy eggs. I don't know, but I certainly did not ask for it. And I got eggs, and that's not great. And, well, the agent, was it wrong? Yes, I did not ask for eggs. It got me eggs. But like, it's not punished for it. So when we think about agents, right, models that will talk to each other and do all of that, we need to first realize that they do things we don't ask them for, and that's wrong. And at least our current training stack does not penalize this in like any big ways. Of course, we'll duct tape it. And like, never bet against scaling in deep learning, right? If you get more data and should build data sets especially to like not buy stuff that the user hasn't asked for, then the next version of the model will not buy stuff that the user hasn't asked for. But if we're imagining a future where the agents go and code the website and repair the site of a bank and hack another site, it's not going to happen that quickly if they can, you don't build the data for every single thing you want to do. So it's not like the models aren't great. Yes, they're great. They can probably code you a website right now. And in a few months, they'll probably make reasonable PRs to fix stuff. But when they're not great, they make mistakes that are extremely dumb. And so yes, you can ask a model right now to make a Windows 95 clone, and it's good. And you can ask the model to search on the internet, and it's also good. And especially like if you do something like deep research, I asked it the most impactful papers on transformers. It's really good, and it gives you a list of papers from that year, and that's all great because it was trained for it. But if you ask it for something that it was not trained for it, and I have the luxury of knowing what it was trained for, so I know what to ask, then it will like very easily, mistake this year for 1921. Or like the mistakes are not the mistakes any human would make, because you wouldn't look for papers from 100 years ago. And for the model, it's just one digit. It's not just, the level of accomplishments is very high. The models can do amazing things, right? They can solve math problems that I find hard, and I was a mathematician, and they can write code that would be not easy to write in that time. And that's all great. It's a lot of value. But the mistakes they make are very bad. And not necessarily bad in the sense they break something, but they're just stupid. Humans wouldn't do this, and especially not humans who can do things at the level the models can. So how do we get there? So, what do? We have these things. They're great. If you have a human in the loop, then it's fine. And since our rollouts with the models, it used to be like you think about these apples and there's 6 of them and you add 5 and it's 11. And all of that was 100 milliseconds and this was good. But since it's gotten so long and now you call some Python interpreter and search and the search takes 3 seconds and it hangs. So now it's taken so long that you can actually call humans in the loop. Like the model, you can give it an API to call something which actually goes to a human who can read it and has enough time to like type in a response. So if you put humans in the loop of the model, that's much better. If you put humans somewhere in the process to verify what the model does, then of course the human will catch all the stupid mistakes and say, well, no, try again here or whatnot, give some feedback. So that's great. And so as I go to my thoughts, human in the loop is a perfect thing for agents today. And also, if you look at earlier technologies that benefited from AI, like if you look at self-driving or translation, you can try to self-drive your Tesla. Be careful, because it may kill you. But you can get a Waymo right here, and it's going to drive you wherever you want in San Francisco. But sometimes it's going to stop and call this human who can remotely take it over. And without this, it just wouldn't work, right? Translation is another example, right? The early transformer, it made very good translation. And I have a friend who founded a translation company with human translators like 30 almost years ago now. And I thought, well, your business will suffer. To the contrary, his business boomed because now the translators can translate much faster, but there is huge demand for a human to actually check whether what the model is saying is right, because still, just from time to time, the model misses a no. And that's a big difference. But your market has expanded. Like, for example, Airbnb now translates every post in every language, which would just not be possible before, but now it is. So if you put the human in the loop, it's amazing. You can do great things, and probably you can have an agent that like codes and the human actually checks it and so on. If you can offer things cheaply, then you can expand demand, have a great business. So that's the optimistic side. But on the researcher side, I feel a little sorry, because weren't these agents supposed to be autonomous? Like, if they're so smart, why are they so dumb? So something is off. Something's, maybe I'm happy because robustness fundamental than we think. So we may have one kind of AGI, like the one that's human-assisted, really soon, because all of these things are possible. There are going to be more of it. But on the other hand, this getting rid of these pesky humans may be harder than predicted quite yet, which maybe is good for us humans, but we'll see. So, that's a DALL-E attempt at a useless mode. So, because a lot of people were building modes of different kinds, I meet a lot of people who say, well, I have this kind of data, is this a mode? Well, probably not. It's like the thing that really seems to work for businesses right now is the humans you have, and if you make them work well with AI, they can actually make the business very well. But if you don't have the people, it still doesn't quite work. So that's a problem. And so yeah, if you want to make great businesses, but also probably great progress with this technology, I think you need to think about your users, right? How can you use humans, or how you can serve users without very many humans? So there was this saying at Google when I joined. It was like a mobile-first company, then it was AI first. I bet you this year it will be agents first. But back in the day, Larry Page made it a user-first company. And I think as the agents are coming and in the AI, I think this user-first mantra is something that's really worth coming back to. Whatever, market at a larger scale is a very good judge. Whatever really works for people, they're going to pay for it. And that's a very good signal. So especially in open source, So I had the pleasure to meet Richard Stallman a long, long time ago. I was also a very avid open sourcer. I tried to make my laptop truly open source to his standards, never managed though. But I do think that probably most of you don't have a laptop that Richard would call open. Is your hardware open? I see a Mac. So, you know, but open source has flourished. Like my phone runs a Linux kernel, heavily modified. Most of my computers happens on Linux servers. So open source has won and lost at the same time. I think something similar may happen to open source AI. Like, I don't think, you know, OpenAI and Google will stop existing, but there are 5 billion people in the world. They're not all going to use the same model. I mean, this is, I don't even think it's a risk. I don't think it's even close, right? The same, not everyone's going to have an iPhone. Not everyone's going to use the same model. And especially the cheap models they're extremely useful, right? And you'll be able to do more and more in cheaper models. So you'll have on-device models, there'll be a lot of open stuff. Probably as we have agents, the more expensive models will start talking to the cheap ones to offload. And, you know, so there'll be a lot of that. But what we still need to solve is this resilience, robustness question. There is a theoretical computer scientist, Moshe Vardi. If you want, you can look up online his resilience versus efficiency talk. He has a huge rant that is very fundamental, that making things that are resilient is tougher and more expensive than making things that are efficient. And in AI, you know, it's a race to the death for efficiency. Like your price per token, tokens per minutes, this is what drives the race right now. It may need to change, because if we really want to replace the human in the loop, you will need models that are much more resilient, right? Your agent, if your Python interpreter fails and your tool doesn't give you the output, can you recover? Can you recover from bigger failures? Do you have a notion of time? Do you know that we are still generating tokens and the user's not looking anymore because it's too late? All of that will be very hard to incorporate in the current systems. And not just hard because we don't have a good research of resilience, but also hard because, like, currently the money follows the efficiency, right? But if you want to do agents that don't need humans in the loop, you may need to pursue that much more. And this may need a much more distributed, kind of slower, a very different kind of system to build, which is an opportunity, I think, as well as a challenge. So that's it on my side, and I'm happy to chat and questions.
Any questions? Do you want to just yell out?
So on the resilience side, do you see it more as a model problem or a data problem or a combination?
Do I see it as a model or data? Probably both and more. I think it's a model problem, a data problem, and possibly also a training paradigm problem. Like RL usually is an algorithm that just optimizes your reward. And if your reward is to do things as quickly and correctly as possible, then it will be as quick as possible. But, you know, maybe to get resilience, you can watch this talk on YouTube, you know. It's like dinosaurs were very efficient in killing other animals, but they're not around anymore. So what happened? Well, changes happen, and sometimes you can simulate these changes in training. It's a little hard, but sometimes you can. It's like I think it's a research problem. Like, we really don't know all that well how to build systems that are resilient. I mean, you know, if you have like RL in simulation, you can add random noise or change frictions, and there are some papers on it, so there are some things you can do. But generally, it's hard, and it may need more research.
I'm genuinely curious how you're thinking about, you mentioned detecting mistakes. So you could either detect mistakes during the inference side, for example, like OpenAI does a lot of optimization around that. You could also do more of a reflective kind of workflow and trying to correct those mistakes. I'm curious, like how your framework, how you're thinking about it in general.
So I think you should try to detect mistakes in all kinds of the reasoning models. They do detect their mistakes on their own a little bit. Like if you look in the chains of thought, even from DeepSeek or OpenAI, you see like tries to do one way, sees, oh no, this doesn't work, and does something else. Or if you uses Python, says, oh, this gives an error, I need to change that. So the basic thing, it does some mistake detection, but then sometimes it doesn't. And if you put an extra model from outside that says, hey, can you find mistakes, it sometimes helps, because it can sometimes help mistakes that somehow the model did not detect on its own. But maybe we need more than that. And so,
I think on that, I think I'm very curious to know your take on the citations, because very often it just gives a perfect answer. You go to the sources to check whether it's correct, and it's, in my experience, 95% incorrect. So why is that happening?
yes, so that's a great example, right? The models cite things, they totally make up things, they look very nice, except they're totally wrong. We didn't train them to do that. I can assure you, we want them to be correct, but it's kind of hard to get rid of this. It feels like it just somehow, the model needs to give an answer. That's a cheap way of giving an answer. It usually somehow passes. Because, so this deep search thing, so there is now a thing called deep research. In chat, you need to click like the blue deep research button. And that is a model that was actually trained to go and verify. So whatever it outputs, like I executed some paper, it outputs a list. Whatever list item it outputs, there is a special model at the other end of the URL that goes and checks whether this output has been, like satisfies this according to this model, which can be wrong, but it's much easier to check one thing than. So after this training, it's much better. You should try deep research. It goes from 95% to like 15 or something. It's not perfect, but it's a big improvement. The problem is, the idea of deep learning is not that we train for every task separately. Like, either you train on the whole internet and you learn everything, or you train on one task, but you generalize very far or something. But if you need to train for every task separately to be resilient, then that's not a great answer. I mean, it's still great in the sense, as the open source community, whatever task it cares about, programming things, you can build data sets, make it resilient in this task. It's a still good business use case. But for deep learning researchers, it's a little unsatisfying. I would want my model to just generalize to be like, and humans can do it. Like, you can do it. You can very easily see that it's a, this is a model that's supposed to be smarter than me, and in many ways what it generates in math and code is, but then a goddamn citation, it doesn't know that it's totally not there. It can go look it up. It should know. And there is a system that tries to check for mistakes, but it kind of lets it pass. Why, right? I mean, yes, if you put effort in this specific thing, and citation is maybe one where there will be an effort especially for that because it's so egregious. But how about the eggs? How about the other thing? Like if you need to specifically solve this every single time, then that's not great. But yeah.
I have a question about benchmarks. It seems like everyone is obsessed with math and coding, perhaps because they're easy to verify. Is there a concern that sort of being so obsessed with those two types of benchmarks are driving only one type of model behavior? Do models that are great at math and coding maybe not generalize well, or do they generalize pretty well? I'd just be curious to get your take on sort of that trend that I've observed.
Yes, so math and coding started because they were easy to measure and easy to optimize. There is now a lot of work on broader benchmarks. And we also have companies like Harvey that do legal and medicine and bio. The surprising thing was it generalized surprisingly well, the reasoning. Like models trained basically on math and code went and did reasoning in law that looked totally reasonable to law people. So the generalization part of reasoning was a nice surprise. It worked better than we would have expected. The problem is still the resilience. So it does a great reasoning, and then just one of the moments, something not a first-year student of law would do, and just so especially in law, that's very bad. But in medicine, making stupid mistakes, it's much worse than you think. Like, huge genius model that does a lot of great things is great, but this beautiful agent future when they're truly autonomous does not exist if they're making such stupid mistakes. And of course, we will scale up. There'll be more agents, there'll be more work, so there will be less mistakes. But I think it's not clear if fundamentally this gets you, because where you want to be is someone like, these mistakes are recognizable by people with no training, right? They're not hard. So we get there without all this broad knowledge, and so we are more general in this sense. If we talk about general intelligence, it kind of feels like this should be solved. The only thing I want to tell you is, agents are great, and for coding, certainly, first of all, you can run the damn thing and see if it's an error. Second of all, there'll be a ton of data and money to do this. So yes, agents will be great, but also, if we don't solve it, then we don't need to fear being truly replaced yet, at least, because it's just too dumb. The same way Waymo, right? It's a great driver. But in traffic, all on its own, it's going to get stuck. So it's the state of the union. That's where we are. I have good hopes that we can make progress, but I just want to tell you, as a researcher, I don't think we're done. We've done great things, but there is a lot to do more.
Thanks a lot for the talk. It's really nice. And I had a quick follow-up on 2 points. From what you mentioned about performance and efficiency, it was easy to see the gains and scale up because of, as you said, the scaling laws, that we can try something on a smaller scale and then we know how it's going to perform when we scale up. So for resiliency, do you think that's a big missing factor, that one, that there is no such scaling, or that if something fixes a model at smaller scale, it doesn't guarantee that it will fix it for the bigger models, and also kind of the failure modes are different. A smaller model will fail at different things than what a bigger model will fail at. So even if I fix something for a smaller model, it's not necessarily, it doesn't guarantee that it will fix resiliency problem for a bigger model.
Yes, I think we don't know if there is a scaling law for resiliency. I also want to point out that we made scaling laws after we kind of knew how models work, already fairly big. So sometimes the laws came after the insight. We'll see. Sure.
In terms for the agency part, that we already experienced a limitation with LLM support on T1 answers. There's 2 AI company here in the Bay Area, 50% resolution rate. And also, fundamentally, if you compress there more than 12 or 5%, you can recover the original back. And also, we stay in the close asymmetry structure, you eventually run out of angle to proximity search, because we cannot create more angles. You think we can overcome those close asymmetry limitations down the road with different math?
So there was a paper about causal asymmetry. I do not believe in that paper. We tried to verify it. It did not seem to show. But the models have problems. And, well, the reasoning models have much fewer problems of this sort because they learn quickly to restate facts and do whatever they need. But they have other, they give stupid answers at times because they have problems, right? It's not some trick that, we missed 2 numbers. It seems way more fundamental. So we'll need to solve these problems. Okay.